All right, my name is Tim Femi, and I'm from the Security and Privacy Research Lab at the University of Washington. I'm going to be talking today about the experimental security analysis of non-network compact fluorescent lamps in the context of compromised home automation systems. This work was done in collaboration with the UBCOM lab at the University of Washington as well. So the abstract from my talk will be we're basically trying to investigate the feasibility of coercing physical harm through the explosion of compact fluorescent lamps to home occupants via an exploited home automation system. And to help us get a scope on this talk, the problem or the questions we're trying to answer are, what physical harm can an attacker inflict on the home occupants, right? And in particular, we'll be focusing on devices with non-network capabilities like CFLs. And in using CFLs and a compromised home automation system, is it possible to remotely start fires, cause seizures, or expose home occupants to mercury and shattered glass? These are questions we'll try to answer. A brief background on home automation systems. I don't know if I have a laser pointer. But I have a plan.
It's right there in front of you.
Oh, okay, great. I have a plan of a house here. All right. I have a plan of a house here, and to the core of the system has to do with the controller itself. You have several examples where you have mesh networks with several sensor nodes deployed around the home, and some of them act as repeaters and delivering packets to distant nodes. So with the controller itself, you could have door locks, you could have dimmers, you could have thermostats or HVAC systems connected to this home automation controllers that provide remote connections over the internet so that users can conveniently, or homeowners can conveniently control appliances in the house over the internet. Home automation systems, just to add to this, home automation systems also work seamlessly with fire alarms and the likes to detect intrusions and fire. Just in event there's something of that sort. So for the projected market growth, we're all familiar with the Nest system. How many people know about the Nest thermostat? All right, great. It's expected to grow at a compound rate of 33% from around 2.3 billion US dollars in 2010 to nearly 9.5 billion US dollars in 2015. This is from the Berg Insight. They also have, numbers telling you how much internet connections that would increase as a result of home automation systems. So what were some of the remote compromising capabilities that we're able to accomplish with the systems? Just to give you an insight, we purchased two brands of Z-Wave home automation systems, and for confidentiality purposes, we'll just tag them as products A and B. We also bought a bunch of sensors around the house to simulate an actual deployment in the home. And some of these sensors or actuators were light switches and dimmers, door locks, thermostats, IP cameras, and the likes. So both products are very similar in the features. They both have a web interface to allow users to control appliances remotely. They also had remote capabilities to control over the internet appliances. The only difference was with the Z-Wave module that they had. One was integrated in the device. The other required a dongle that you had to buy separately. So for the vulnerabilities that we discovered with these systems and actually exploited, we noticed that product A was susceptible to cross-site scripting attacks. We were able to embed JavaScript code to add a fictitious user with admin privileges while ensuring the stealthiness of our attacks on the systems. With this way, we had direct access to the control panel to turn on light switches remotely over the internet. We could turn on up. We could also control HVAC systems. These are power-hungry devices. We could unlock doors. We could do whatever we wanted to do with the home automation system. The other thing was with insecure HTTP, where if you were on the same network with the homeowner, you could capture packets or eavesdrop on packets, credentials, and extract credentials, login credentials, which would enable you to get access to the system at a later time or instantly. The other thing with Product A was very prone to a lot of attacks, as you can tell. It had VNC server with running on a high numbered port. The issue with that was they had a default password of admin, and if you're like a do-it-yourself like myself and non-technical, you may not know or you may not be aware of the fact that you had a VNC server running on that, and so you could get direct access to the system and control whatever you wanted to do. Product B, on the other hand, was found that it used insecure cookies. They did not attach any expiration time or date to it. If you know what the cookie value was, you could just add it to your browser and have complete access to the control panel itself without login. So what are the implications of these vulnerabilities? An attacker can remotely control appliances and actuators in the home. This has been shown by Fuladi and others. They just published work in Black Hat. They were able to control light dimmers, switches, HVAC systems, alarm systems, door locks. We also did the same thing, except that the attack vector was different. They actually compromised the Z-Wave protocol stack. The other thing is an attacker can deal feeds of webcams without the homeowner's consent. This is especially creepy if you think about having kids and putting nanny cams in your rooms and the likes. It was very insecure in this regard. But the important part of our talk, I think, of my talk today is non-network appliances like CFLs are not exempt from an attacker's manipulations, right? If you take a moment back and think about it, manufacturers of these appliances do not think about users using devices like this in this context where you can remotely manipulate them, and we do believe that manufacturers do not test extensively these scenarios of operation, and it's more likely for an attacker to leverage this and push the limits of the operations to regions that have not been tested against. So why would an attacker choose CFLs? It's cheap. It's out there. Everybody is switching to CFLs these days. Incandescent lamps have been phased out for CFLs due to their energy efficiency. This increases the pool of possible attack targets that an attacker could go after. The other thing is CFLs have more potentially vulnerable complex circuitry than regular incandescent bulbs. They have electronic ballast for regulating the amount of current flowing through the CFL itself. There's a good chance that we could push the operating points beyond what has been tested against with our attack scenarios. The other important point is standard CFLs are not to be used with light dimmers as they may trigger fires. There have been instances of this in the news. I will make some core assumptions or core setup later in the next slide as to why this may be a problem. The other issue is most CFLs contain about 3 to 5 milligrams of mercury as this a potential source of harm for the home occupants. So our core assumption is the homeowner has ill-advisedly connected a non-dimmable CFL to a remotely controllable home automation dimmer, right? Again, keep in mind, the fire department has issued warnings that people should not use standard CFLs with dimmers, but people may choose to ignorantly ignore this or stubbornly do so. And we've seen instances of this that have caused fires in homes. So what was our approaching method? To start out the experiments, we needed to ensure safety. again, I like that the risks, fire, glass, mercury, right? So we needed to anticipate and be adequately prepared for the hazardous materials. And we set out to do this by using this structure, the plexiglass structure that we designed, and we thought it would, keep us from any shattered glass that might have resulted from our experiments. As it turns out, this is not an effective way to keep us safe from mercury exposure in the event that that happens. So we took a step back and talked to people in the department, and we were lucky to have people, a wet lab that was designed for this purpose to properly contain mercury and dispose of mercury in the event that it's leaked. So they gave us this glove box, which did just that. It was well ventilated. And we proceeded to do all our experiments in that. And keep in mind, we are EE and CS majors. And we had to get expert advice. Yeah.
Nate from IU. Question: if shattered glass, because you're looking at sort of like a bio-sealed environment with a glove box, were there precautions taken to make sure the gloves did not get compromised because of shattered glass?
Right. Yes, we did a couple of other experiments before, just playing with the lamps itself, and we ensured that the region that the latex gloves were well covered, just in case something of that sort happened. Yeah. Thank you. So the glove box was, provided that insulation or that protection from those dangerous materials. It also has a fire extinguisher just in case. So we also wanted to know how much current was flowing through the lamp itself. We wanted to see anomalies and the signals we were generating and what effects they had on the CFLs. And to help us do this, we had a Physix current sensor that acquires the root mean square value of the current through the CFL in real time. Also use the interface key, which captures 1.5 samples per second. We also wrote a real-time plotting tool in .NET just to help us visualize, how much current was flowing through it. And this is what it looked like. It was pretty basic. The time is in milliseconds, and we had the current in amps. So signal generation. What did we do to generate the signals? We utilized the OpenZWave.NET libraries to write a bunch of scripts to generate our signals. We did not perform an end-to-end test over the internet, as that wasn't the focus of our work. We wanted to see what kind of signals could be applied to CFLs accustomed to pop or catch fires or release mercury. Right? We also used the ANC stick static update controller shown there in the picture beside it. It has an integrated Z-Wave module. So for the signal types, we had 4 signals. Signal A was a train of periodic triangular pulses that basically simulated an individual turning the dial of a dimmer all up to the maximum and down to the minimum at a fixed rate. So it was periodic in that regard. We played around with the levels and figured that it was more effective to have the levels somewhere close to the onset of visual fluctuations of the lamp to cause it to fill quickly. The other one was with periodic rectangular pulses. Well, we're basically just toggling the CFL on and off at a very fast rate. I'll talk more about the signal later on.
Question?
Yeah.
Is there anything with physics behind those waveforms that you pick those?
So for signal A, we just
I mean, those signals have caused failures in other devices.
right. So I think we went off of the assumption that if you toggle something on and off at a fast rate, you're gonna at the simplest case, you're gonna reduce the lifetime of the product, right? We're gonna see what variants could we come up with that could cause more harm through the CFL itself. I think we just went off of that and came up with variants. Thank you.
So, follow-up question?
Yes.
I lost the train. Are these signals to the controller, or is this what the power looks like going?
No, this is the Z-Wave dimmer. We just altering the dimmer level. So you have a range of 0 to 100, and you can vary the signal, the level based on the Z-Wave dimmer.
So that's the signal to the dimmer,
Right.
and that's not what the power output looks like.
That's not what it looks like. I will show you that. I'll show you a video of that later. So signal C, we wanted to introduce some randomness to the whole thing, right? What we did was use a random number generator with a Gaussian distribution, and we basically compared it to a threshold, and based on if it was higher than the threshold or not, we would increase the dimmer level on the CFL. And then the last signal we applied was signal D, which is a combination of signal A and signal C. What we did was, for the normal operation, we had the generation of signal A, and then we randomly generated current spikes based on some random number generator, just to introduce, random burst of current flowing through the CFL. And there are lots of possible, signals that you could generate. Think of, playing with the threshold and seeing what effect it has on the signal. Like you said, the level for signal A was chosen to introduce an offset was introduced at the onset of visual fluctuations on the lamp itself. We've not explored a wider range of possible signals that you could generate. Did you have a question?
I'm better for the end.
All right, cool. All right. So just to explain signal D, the generation of signal D, we had like an initialization sequence, and then we went ahead to generate a random number. And based on the random number, we compared it to a threshold, and if it happened to be less than the threshold, we'd go on with the generation of signal A. And we just repeated the cycle over. Now, in the event that the random number that was generated was greater than the threshold, would proceed to generate another random number to denote the duration of the spike, the current spike, right? And we would set the dimmer level to maximum during that duration. And then at the end of, and they would periodically check it and say, oh, as the current duration expired, and if it's expired, would regenerate a new number and just go around the circle or the loop. And if it hasn't, we just set the dimmer level to a maximum level. So that's, in a nutshell, how signal D worked. So I have a video here for the actual voltage across the CFL during the course of our experiments. This is an oscilloscope with showing 2.5 cycles at 60 hertz. The tree goes set to 60 hertz. And we'll see this in just a second. And that's the y-axis is the voltage, while the x-axis is the time. Okay. So this is with signal A. You can see the pulse width modulated signal, and over time, it's like we're increasing the pulse width at a fixed rate. It's like we're ramping it up to the maximum and to the minimum. So it increases the pulse width and decreases it at the same time. For demonstration purposes, we replace the CFL with an incandescent bulb, just to be safe. And you can see the effect, and that's a Z-Wave dimmer. So you can see the pulse width increase and decrease. That was just the operation for signal A. Now, if you connected this to an actual CFL, you'd see it fluctuate at some unsteady state. Okay.
Did you put some calculator here because the voltage across two
Right.
boards, 4 boards, and
Yes.
not on your lamp?
What we did was we used a step-down transformer to decouple the oscilloscope from the actual CFL. I'm not going to show signal B because as we found out, it may induce seizures, and for safety reasons, I will not show that. For signal D, uh, that's the current monitor, by the way. You can see random spikes in the current monitor. What we're basically doing is go ahead and generate signal A for the normal operation, and then randomly ramp up the current through it. And you would see from the oscilloscope, this is like the normal, and you can see like the rapidly increase pulse width. But the normal region is around this region where I'm just ramping up the current to a fixed level for signal A. And then you'd have occasional increases in the pulse width of the signal. Yeah.
For signal B, how did you protect yourself from getting seizures?
So we used disposable trash bags to cover the glove box so that we would not stare directly into the glove box during the experiments. Yeah.
You didn't find out about seizures by a direct result of your lab, I don't.
Well, I think it was an afterthought when we thought about the frequency at which we were toggling the lights, and they were like, oh, it's probably a good idea to just cover this, to knock us. Yeah. Good question. So results. We were able to get some CFLs to chart, some components, the BJT to be specific, bipolar junction transistor in the CFL burnt out. In this case, you can see I don't know if you can see the charring around this region in the device. This plot is from the current detector. So this is the result of one of the experiments we're doing where, running the signal A on the CFL, and we noticed at a particular point that it was about to fail. So what I did in this situation was I disconnected the CFL from the dimmer and connected it directly to a power outlet, and that's why you have the spike. But the interesting part of it was it actually resulted in a pop. We could hear a pop from the CFL, and we could see that it was charred at the end of the experiment. And this led us to take a step back and revelate how we were conducting the experiments. So we thought this is how signal D came into existence, actually. So we thought, how about we introduce random spikes into the signals at random times, and have the normal operation of signal A. And that's what brought about signal D in the first place. This is some time to failure for the CFLs. We did a bunch of test runs, but these are the results of the one we actually accurately had timings for. We found out that CFLs either give way. By give way, I mean normal failure where it just burns out without any pop or visual or auditory observation. By the pop, I mean that you actually hear something and you actually see something going in the CFL. So the time to failure. One thing I want to point out is it was very inconsistent due to processor design variations. We found out that for even similar brands of the CFL, it took different times to fill. And we were lucky to get, well, I won't say lucky, but we were able to get some CFLs to fill in like 18 minutes and some to fill in over like 7 hours. So the experiments were quite interesting when we got a result that popped, but also painstaking and the number of hours that we had to watch it sometimes. The other thing is I have I like it here, the CFL 8, showing that we the plot I had in the previous slide was basically the result 8, where we disconnected the CFL from the dimmer and connected it to a direct power outlet. And then we can see that in for the CFL figure for the lamp 10, we were able to get it to cooperate in 1.5 hours after applying signal D to it. So applied signal effects. So we at the end of our experiments, we were able to come to a conclusion that signal A was effective in getting the CFL to pop. So was signal D. For signal B, we concluded that it was able to cause seizures at the rate that we were at the rate at which we were tolerant at. For mercury, there's no cost-effective way to detect it or quantify how much was released. So whenever we did our experiments, we made sure that it was enclosed and properly disposed of within the glove box itself. There was no instance of shattered glass during the course of our experiments. And that just summarizes the effects that those signals had on CFLs. So for future work, we definitely want to test with a larger sample size. Would love to investigate with more signal types. Like I said, you could play around with a lot of variations, different different distributions for the random number generator, or different thresholds, or different voltage levels that we were running against. Would also want to know the effect of the experiments on the temperature of the CFL and its surroundings. So one thing that would like to point out is even though we did not cause a fire, but think of a scenario where you had a lampshades around the CFL that could combust easily and cause a fire. Those are things that you can think of, and it's been nice to know what effect our experiments have on temperature. Would love to detect and quantify the amount of mercury released, and we'd love to do an end-to-end analysis on compromised systems over the internet. So lessons learned. Experimentation with cyber-physical systems can be expensive, time, money, and it requires constant monitoring. When you think of computer science experiments where you can run simulations overnight and come check your results, we did not have that. We did not have that ability because there was a potential for fire, and we had to monitor it for like as long as 7 hours in some cases. It's also very expensive in regards to money. Think of what you need to purchase, the setup, what are the safety plans and measures you have in place. Failure times of CFLs were highly inconsistent due to the process and design variations, as alluded to earlier. Even if you had the same brands of CFLs, the times to failure were largely inconsistent. Yes.
Due to which process? Are you saying manufacturing process?
Manufacturing process. Manufacturing process on the device.
So that's a hypothesis at this point.
That's an hypothesis because we believe we're able to prove that because we're the same brand, right? The same.
Didn't have a large enough statistical.
Yeah. And you don't have ground truth for why they failed.
Well,
you don't know whether it's a processing problem or a design problem or what the problem is.
So for design problems, we said we bought 2 different brands of CFLs, right? They had 2 different designs, and we tested against that, and they had different times. In fact, if you looked at the table, you notice that one particular brand failed with the pop, and the other did not. We kind of attributed that to the design variation. For the process variation, we had the same brands, and they had different filling times. So I guess it's an hypothesis, but
I think it's a hypothesis.
okay, that's fair enough. Did you have a question? Okay.
So I was just wondering, you're discussing expense here. Is it just expensive according to what we normally do in security, or expensive according to what? Because this still seems pretty cheap compared to bio related, the usual people we see doing lots of physical experiments.
Well, it's cheap. It's relatively cheap compared to other computer science experiments or research. we had to buy a bunch of different nodes just to simulate the home or deployment in the home. We had to do other things, safety measures for one. No lab wanted to just immediately accept, oh, come to experiments that could result in a pop or a fire in my lab. These were things that we had to take into consideration while doing this experiment.
So how do you think dimmable CFLs respond to this sort of test? I mean, are they, do their specs kind of like state that they really shouldn't fail under the sort of signals?
Well, we didn't try with dimmable signals, but it'd be interesting to see their effect on them as well. I believe there'll be a region of operation that you can push them to that may result in a failure, but that'll be interesting to see. Oh.
How did you plan to like stage an attack into the
So we initially showed. So the question was, how do you plan to stage an attack into the home automation system? We basically demonstrated that we were able to embed JavaScript code and gain access through cross-site scripting attacks to the home automation system. What we've not done yet, which was not the focus of the paper, was to conduct a full end-to-end experimentation with CFLs over the internet, which is something we had to do. So the last point I had was Signal B had the potential to induce seizures due to the rate of fluctuations. We're doing it at a very fast rate, and we had to cover it with disposable opaque bags to prevent that from happening. And if you think about it, it's not really. You may say it's not really an issue, but if you have someone who's prone to seizures, not expecting CFLs to induce them, and an attack against access to the home automation system, you could cause that person to suffer a seizure, either normal or non. Yeah.
Did you have you reported the security vulnerabilities that you found to the home automation system manufacturers?
Yes, we did.
And are they receptive or understanding?
We've not gotten a response yet, but we informed them about the vulnerabilities that we found in the system.
Because it seems like with your paper and Black Hat paper,
Yes.
that it's just sort of waiting to happen. I mean, there's an ad on TV, which,
Right.
I love, the family of the cabin
Right.
and the kids stop by the house and then dad sits there and turns everything on and off. I mean, I have, teenagers and 20-year-olds who routinely leave the house in pretty much that state.
Right.
And I look at my husband like, we need this.
Right.
But now, if this becomes, sort of known knowledge, then that ad plus this kind of paper is sort of, an invitation for the hacker.
It's a very good point you raised. I think there is so you look at the benefits. It has a huge convenience factor to it. But I guess there's a point where you have to step back and reevaluate things from a security perspective and say, is it worth it? Well, it has this huge benefits, but what are the costs I'm giving up in terms of security and privacy? And you can evaluate that and decide whether or not to get it.
I want the manufacturer to put
Right.
the security holes.
It's nice to bring this to their they should be made aware of this so that they can make it more robust to attacks like this and future undiscovered ones.
Just a comment, I guess once you have some system connected to the internet, there's no guarantee that you'll be totally secure.
All right. Was there a question somewhere? Okay. So related work. I pointed out earlier that Fulati and others compromised the Z-Wave protocol stack. Denning and others also demonstrated that the physical exploits to robots used in the homes. They were able to manipulate them, get live feeds from them as well. We and others compromised this is the work that was done in Colombia. The compromise printers through a firmware update modification, and they were able. I think they claimed that they were able to get the printer to char papers in their work. Checo and others demonstrated the compromise of automobiles, where they were able to disable brakes remotely, They were able to turn on the lights in the car, record conversations, eavesdrop on conversations in the car. These are some related boards in this area. With this, I'd like to thank Professor Carl Boringer for granting us access to his lab. We did all the experiments in his lab. Carl Kosher for his feedback on feedback and help with the experimentation. And other members of the Security and Privacy Research Lab, one Dr. Perry Gates, and the LISA community, and anonymous reviewers for the feedback on this work. With that, I'd like to summarize and say our experiments show that non-networked appliances like CFLs are vulnerable to remote manipulations by an attacker. And this should be something that people should start taking into consideration, especially home automation designers, homeowners, and researchers. I'd also like to, at this point, open the floor for questions and discussions. I think one thing that comes to mind is it possible to obtain similar results with binary switches from what we found out? And feel free to, this is a discussion, feel free to interject and raise up your concerns. From what we found out, it's possible to do something of this sort with signal B, where we toggle the light switch, the binary switch on and off at a very fast rate. But we've not done experiments in this area. I would also want to open up, just a discussion. What other non-networked appliances may be vulnerable, and what appliances would you like to see studied? If you have anything, yes.
So, Pete Dinsmore from APL, picking up on a comment Greg made earlier, I'd love to see a little bit more work on the physics of the physical side.
Okay.
Because, you popped it, but what was the physical phenomenon
Right.
that actually broke?
Mm-hmm.
And that would then inform, what do you need to, you almost need to go backwards.
Mm-hmm.
What's the physical phenomenon I want? And then how do I induce it with the waveforms, rather than trying a bunch of waveforms and seeing if they do something.
Right.
But do the damage assessment and see, well, what, was it a transistor that overheated? Was it a junction that broke?
Right.
Was it something in the bulb itself that failed?
Right.
What's the failure analysis? And then how do I induce it? And that would make a much more focused experiment, and also much more focused mitigations.
Right.
Do I mitigate it in the circuitry in the bulb itself or in the controller? Because then we can actually tell the controllers, don't allow this situation to occur.
Right.
And even if they get broken into, there may be safeguards in the controller about the physical aspects of what it was doing. Because that's, in the end, the data you had was all about the physical effect rather than the side
Right.
effect.
I completely agree. It would take, reviewing the schematic and analyzing what the normal operations are and what the, boundaries are, and what we can push it to do. I completely agree with that.
Yeah. There's a potential trivial defense to consider with this attack too that might be worth looking at poking holes in. That is, well, I'll just use LED bulbs and everything, and those potentially will have some circuitry issues again.
Mm-hmm.
You don't have to worry about the mercury,
Right.
And you still have huge power savings. Now, you could certainly denial of service the individual's budget if you blow a bunch of their LED bulbs because they're not really cheap. But the health risks,
Right.
except for maybe seizures, are lower.
Okay. Yeah, that sounds. We actually considered doing some experiments on LED bulbs, but we didn't get there yet. We did not get there at the time to publish the paper.
Your previous slide lists a bunch of other successful attacks, and your discussion slide suggests that maybe there's more attacks that could be successful, and maybe all that is true. What seems missing here to me is the extraction of some kind of scientific principle that could be investigated that threads its way through all of these things, and somehow unifies all of these things. Because it just strikes me that it might be more critical to figure out what the scientific underpinnings are, that it would be mean, I need to know this and getting it to core scientific issues.
Yeah, I completely agree. So, but I think when we started out this work, we set out to identify. We set out to identify uh, factors that may drive the community, the manufacturers, you know, homeowners to consider what risks are associated with connecting something that was designed to be contained in the home to the internet. What manipulations can, you know, what remote manipulations can bring about, or what results that you can get from a remote attacker's point of view. I agree with you on the fact that yes, we need to identify the scientific principles and the physics behind all of this to make it more robust. Yes, we will get there, but I think this is an initial work into, oh, these are possible scenarios that you could have with the systems connected to the internet, and how do we go about, you know, ensuring the safety of homeowners.
Well, if you're looking for something in the form of a product wording, you can look for guidance from the tobacco industry and see what they went through.
So to follow up on that is this idea of sort of getting to not necessarily in my case talking about this grand thread, not using physics as the grand thread, but I've evangelized on this a couple of years ago at a large industry security conference. And the idea is, as academics, we have a very useful position because we are not reliant upon immediate sources. In some ways, we're not relying upon the immediate profit line that a lot of organizations and security researchers are reliant on, that usually causes them to do just straight attack research. And when we see, I think what would be useful as a thread, and what we have the leniency to do as academics that a lot of the industry security researchers can't do, is that when we have studies like this, we don't really have a good framework of judging the risk of these sorts of attacks. So that could also be this nice universal thread as you go through it. Because when we talk about these, we are proving a binary. We're just saying, yes, it is possible to do this. But just saying it is possible to do that does not allow me as an individual to make an educated decision on how to mitigate the attacks.
Right.
Because what are the costs am I going to ensue protecting my network, the cost of education, money, et cetera, and as academics, we can look into that. But the people who usually produce a lot of the attack research just end up doing the binary research because they work for a concerted security consulting firm, and doing the binary research is, fits in the product cycle, it's great PR, et cetera,
Right.
but they just can't look beyond the surface level. They just don't have the time.
Okay.
So actually, since we're going to break for lunch here, I just want to make a comment since Lucy wasn't in the program committee discussions. I want to share just a little bit about what we saw valuable in this paper and why we thought it was appropriate for this conference. And it really was driven by the methodology, and that's actually why Dr. Gates was involved in helping shepherd the paper to really bring out the notion of what was the methodology, because the notion is so that it can be reproducible, so that you can do the sort of statistical test to determine whether or not a particular factor is significant. But we thought the real contribution was let's nail down the methodology, get that documented through the workshop, so that it could be used. And it's so that notion of nailing down the documents, nailing down the methodology, then becomes a reference for other people saying, okay, if I want to investigate this area for attacks, here's something that I can look at and say, okay, I need to create a methodology like that in order to do an effective evaluation. So I just wanted to add that before we go.
No, thank you, Greg. Yeah, so I wasn't involved in discussions, but I do think that since I have the mic, I have to do it. I'll take the opportunity to say that there's a number of directions we could take this conversation. One of which was just how do we think about doing security with physical artifacts like this safely? When we may not a priori actually know the risks. So we knew about explosions, we knew about mercury, we knew about potential fires, but things like seizures, what steps does one need to take to understand the thought of everything? I think we do have a few minutes left. So I was noticing, kind of questions from a few people, but I suspect that lots of people also kind of, might have thoughts about this. So I want to do another group activity. Yes, Okay, fine. But we're going to do that anyway. We're hopefully find someone you haven't talked to yet. Introduce yourself and come up with one idea, some takeaway message or some direction that you would like to see happening in this broader space. So takeaway message, what have you. So you just discuss with someone you haven't discussed with yet. We'll get to everyone eventually. Okay, so that was about 2 minutes. So that was about 2 minutes. So we're all going to come back together as a group, and I'm curious to see if any other questions arose or things that you want to ask Lupe in response. So yeah. Yes.
Aren't you glad to see that people are so inspired by your group activities?
I am, yes, I am excited to see that.
Hey,
Good to hear people discussing.
Yoshi, also, there is a capability for the people who are remotely viewing to ask questions if they want.
Yeah.
So we haven't gotten any questions from folks remotely, but if they want to ask, they can, and we do have someone monitoring their chat sessions.
Oh, great. Okay, and they know that, so they can ask.
Hopefully they do, but
Okay. So in the 7 minutes left, I'm not sure exactly. I know. Yes.
One outcome that I found interesting in this is that having watched this paper as we've gone through the acceptance procedure, getting up to this point, was the change in tenor from going from this is an interesting result, which is an important result, that's what the paper's about, to what kind of higher level abstractions can we start to draw? And it was you that brought up how do we as academics start to say how do we prevent this kind of thing from happening in the future? And that's the kind of thinking that we're trying to engender in this whole conference is moving from, excuse me, this is not pejorative, but cute tricks. It's an interesting, fun result. But the end result is what's the science behind it and how do we change that? And so that's when Kerry Gates got involved in this, her interest was in trying to make that move through, just understand how is it preventable, what's the science, how can you predict it, how can you control it, those kinds of things. And so we're doing that in the course of this paper and the modifications that you guys are working on with Kerry Gates before you publish it, then we're doing exactly what we're trying to do, which is to move from interesting results to broadly applicable principles that underlie that result.
Thank you.
Great. Any other questions or comments? Yeah.
Well, so my comment was, you said, these kinds of experimentations are very expensive. You listed the related work.
Right.
I mean, kind of following up on what Ed said, I mean, most of the cyber physical kinds of experimentations that are being reported in these conferences, right, are very sort of one-off, very dependent on the conditions and set up in one particular laboratory. And so the question is, leading into our after lunch discussion, how can we make these more repeatable, analyzable, you know, where's the trade-off in the range of simulation and emulation to real, you know,
Right.
what value can we get by not actually blowing up the light bulb, but like Pete has said, by bringing in physics, you know, so we have more theory behind it and more abstractions.
So very, very good comments. And then I would add to that probably, you know, doing so wisely in the sense of, you know, for like the car work, for example, you know, we wanted repeatability, we wanted it to be scientifically valid, but we also didn't want someone off the internet to just download the code and start hacking cars. So, you know, what's the right level of repeatability scientific? I think these are all very good points.
Actually, to tie into that, and the fact that you mentioned you gave the vulnerabilities to the manufacturers, some legal implications here. When you do that, what is our level of due diligence that we can then go back as scientists and say, look, we were due diligent, we sent these to the manufacturer, they did not fix them, but because this is a scientific endeavor, we want reproducibility, we have to publish our code. I argue code publishing is a requirement of proper reproducibility. And so at what point can you legally shield yourself from any ramifications? Because while you were due diligent in protecting against these bugs, the manufacturer, however, was not, and just sat on the reporting of the vulns for who knows how long.
That is a good question, and I suspect that the answer might depend on the situation.
Yeah.
You know, I think another thing of kind of doing our, you know, job of trying to protect manufacturers that, you know, is a discussion point is we actually said product A and product B, and we didn't point fingers at names, and that was because we didn't want someone to, you know, we didn't want to facilitate the exploitation of systems. But on the other hand, someone might argue, well, we actually need to know, you know, which are these particular products we looked at and so on. Gosh, you know, I think there's also, you know, one needs to consider both, not just, you know, the scientific reproducibility, but, you know, the actual legal implications in, you know, trafficking in attack code, you know. So, you know, I think these are very good questions to consider. But yeah.
I just want to share, I guess my view of this research. First of all, I love this. This is, you know, so fun. My background is, my undergrad is in electrical engineering, so I felt really at home here. This was wonderful, probably, you know, one of the, you know, most at-home presentations I'll have. And I'm also taking courses in the reliability engineering department. My advisor's in that department, and this fits, you know, squarely in those fields. And I just wanted to point out that there is literature in reliability engineering where you will see models, typically of like a light bulb model for what is the time to failure of a light bulb. It's like the textbook example that they give. Yeah. And so I would encourage you to just look at what's out there, and you can see how your data fit into that. There's also models for accelerated testing, so that you don't have to, you know, wait 18 hours.
Right.
In some of these. There's also models for.
That'd be nice to have.
Yeah, and it's out there. I just wanted to point out to you. There's also models for what they call the censored data, where it fails, but you don't know when in the time interval it failed. You came back the next morning,
right?
And it was broken, and that's again out there. There's textbooks on that. We have a course at the University of Maryland. It's called the Physics of Failure, and that fits right into this kind of stuff. You can get into the actual device. You mentioned the POP, and now I have to go back to my undergrad lab days in, you know, the electronics lab, and I actually was looking very carefully at the picture that you showed of one of the CFLs, and I could recognize electrolytic capacitor. That's a cylindrical device with like blue and black in there.
Actually, at the board, I could pass it around if you guys.
I'll pass on that just because of the mercury.
No, but it was shielded. We didn't break the container.
Okay,
so it's just the ballast itself.
Maybe then. Maybe. And so just to read some physics on that, typically if you're being, you know, badly behaved in your lab class and you want to make the electrolytic, you know, capacitor pop, you reverse bias it, and that'll cause problems. My guess is that wasn't exactly what it was, but there's also the property that the charge on a capacitor is a state variable, meaning it can't change instantly. And so as soon as you showed that plot and it said, oh, we had a surge,
right,
and then we heard the pop, I thought, oh, that's so electrolytic capacitor just
right.
do that, you know.
So keep in mind, just to add to that, we don't have access to the light bulb itself. Well, all we're doing was just remotely, and I think it made it difficult. So you mentioned reversing the polarity on the capacitor. if we had actual access to it, to the DMAR, to the CFL, maybe there would have been ways to do that. But we're doing all of this like remotely, and we're assuming that the attacker doesn't have access to these things.
Understand, great. Anyway, thank you for letting me add that.
Yeah,
I really
thanks.
enjoyed this.
Thank you very much.
One last comment. That kind of extraction that you're talking about is exactly what we're after, because what we're trying to get to is, let's take ideas like from a CFL study, like what you're doing. Can we extract things that we know are vulnerabilities, and we can apply them in situations like SCADA control, for example, or implantable medical devices? I mean, those are higher risk or higher consequence kinds of things. And so can we learn something in a cheap and easily repeatable environment, CFLs, that applies to very highly critical kinds of applications later on? That's what we're looking for.
Right. Thanks.
Great. So let's thank Topet.